Hey, future orthopedic surgeons, are you ready for those big exams?
Mm.
The FRCS and all that.
Yeah, those postgraduate exams, they
It
can
can,
be a bit daunting.
yeah, especially the statistics part. It can feel like a whole other world, right?
Definitely.
But today, we're going to try to make it a little less scary, a little less daunting.
That's right.
We're going to dive deep into uh, those essential statistics concepts that I think you really need to know for your exams.
Yeah, you've got to have them down.
We're going to be using the Ortho Made Simple notes from mokingren.sg
Great
as our
resource.
guide.
Yep.
These notes were actually created by Dr. Mok-Ying Ren.
Oh, yeah, I know him.
Yeah, he's a sports surgeon over at National University Hospital in Singapore.
Right.
And he aced his FRCS just a couple years ago, back in 2022.
So he knows what he's talking about.
He definitely knows what he's talking about.
For sure. All right, so we're going to break down everything from those like really basic data types to even getting into, interpreting research papers
Wow.
and even designing your own studies.
That's great. I mean, it's all about building, I guess, like a strong foundation.
Absolutely.
And then learning how to actually apply these concepts in the real world of orthopedics.
Yeah, you're going to use this stuff every day.
Okay.
So it's good to have a good grasp on it.
So let's start with the basics.
Sounds good.
You've probably already, come across different types of data
Oh, for sure.
in your clinical rotations.
Absolutely.
How can we categorize them in a way that'll help us choose the right statistical tools?
Right. You need to know what you're working with. So one way is to think about whether the data is it categorical
Hmm.
or is it measurement based? So categorical data, that's when you're putting things into groups. Like think about fracture types, right? Or different kinds of implant materials. Or even something as simple as smoker versus non-smoker. Now, with measurement data, you're dealing with actual numerical values. So things like range of motion, bone density, or those patient-reported outcome scores.
Okay, that makes sense. But I feel like within those categories, there's even more distinctions,
Oh, absolutely.
right? Like nominal versus ordinal data. What is that all about?
Yeah, so nominal data is that categorical data, but there's no real order to it. Like
Oh,
there's no ranking. For example, classifying fractures as open or closed.
I see.
That's nominal. Now, ordinal data, on the other hand, those categories do have a ranking, a clear order. Think about pain scores, right? A score of 8 obviously means more pain than a score of 4.
Okay, so it's all about really understanding the nature of the data before we can even think about analyzing it.
Exactly. You've got to know what you're dealing with first.
And then there's this concept of normal distribution,
Right, right.
which is important because it kind of determines which statistical tests we can use.
It's like choosing the right tool for the job.
Yeah.
So when we talk about normal distribution, picture that classic bell curve, like the one from basic stats class.
Yeah.
It means that the data is symmetrically distributed around the mean. So most of the values are clustered right there in the middle, and then fewer values as you move out towards the extremes.
Okay.
So like height and weight in a population, those are classic examples of data that often follow that normal distribution.
So it's like a nice symmetrical bell curve. That's what we're kind of aiming for.
Yeah, that's the ideal scenario.
Okay.
But it doesn't always happen that way.
What happens when the data doesn't really fit neatly into that shape?
Right. Well, sometimes data just isn't that neat and tidy.
Okay.
That's when we start talking about non-parametric data. It doesn't follow that nice bell curve pattern.
Okay.
And the mean, the median, and the mode, they might not be all nicely lined up. Think about things like the length of a hospital stay after a joint replacement, for example.
Yeah.
Some patients, they recover quickly, they go home early. Others, they might have complications and have to stay longer. And that can create a skewed distribution.
So how can we spot a skewed distribution? Are there any red flags we should be looking for?
Well, one clue is if the mean, the median, and the mode are all different.
Okay.
In a perfectly symmetrical, normal distribution, they would all be the same value.
Right.
But if the data is skewed, those measures get pulled in different directions.
All right. So let's say we figured out what kind of data we have.
Yeah.
Normal, non-parametric. What's next?
Well, then we need to choose the right statistical test. It's like choosing the right surgical instrument. You wouldn't use a hammer to insert a screw.
Yeah, that's a good point.
Oh.
So how do we choose the right test?
Well, for data that follows a normal distribution, we've got a pretty powerful toolkit at our disposal. Tests like tests, ANOVA, Pearson correlation, these are all valid options. But if we're dealing with that non-parametric data, we need to switch gears. We need different tools, things like the Mann-Whitney U-test or the Wilcoxon sign-rank test or maybe the chi-squared test.
That's a lot to remember. Are there any tips for keeping all those tests straight?
Well, one thing to remember is that those parametric tests, like the t-tests in ANOVA, they're generally more powerful,
Okay.
but they come with stricter assumptions about the data. Non-parametric tests are more flexible, but they might not be as good at detecting subtle differences.
Got it. So choosing the right test depends on the data and what we're trying to answer with our research.
Exactly.
Speaking of research, let's talk about visualizing data. We see all these graphs and charts in research papers. How do we make sense of all of that?
Visualizing data is crucial, and not just for understanding research papers, but also for presenting your own findings. One powerful tool for visualizing non-parametric data is the box and whisker plot.
Box and whisker plots. Okay, I remember those from med school, but it's been a while.
Yeah, they're really helpful. Think of it as a visual summary of the data's distribution.
Mm-hmm.
So the box itself, that represents the middle 50% of the data.
Okay.
And then the whiskers, they extend out to capture most of the remaining data points. And then anything that's really far out there, those outliers, those get plotted individually. It gives you a quick snapshot of the data spread, central tendency, any potential outliers.
So it's like a quick visual checkup for our data.
Yeah, exactly. A quick way to get a sense of what's going on.
What about those ROC curves?
Oh, yeah.
I know those are important for, evaluating diagnostic tests,
They are?
but I always get kind of lost in the details.
ROC curves are all about understanding the trade-off between sensitivity and specificity.
Okay.
They help us visualize how well a test can distinguish between people who have a certain condition and those who don't.
So remind me, sensitivity is all about correctly identifying those who do have the condition.
That's right.
And specificity is about correctly identifying those who don't.
You got it.
Okay, good.
A sensitive test is like a wide net that catches most of the fish. But it might also snag a few boots along the way.
Okay.
A specific test is like a spear. Very precise, but it might miss some of the fish altogether.
That's a good way to remember it.
Yeah.
So ideally, we want a test that's both highly sensitive and highly specific.
Of course, that's the dream. But in reality, there's often a trade-off.
Right.
The choice of the test, it really depends on the clinical context and what the consequences are of a false positive versus a false negative.
Okay, this is all starting to make a lot more sense now.
Good.
Let's move on to the big leagues. Meta-analyses.
Mm-hmm.
I remember encountering those in journals, but always feeling a bit intimidated by them.
Yeah, they can seem complicated, but meta-analyses are really valuable. They combine data from multiple studies, so they give us a more comprehensive picture than any single study could provide.
So it's like getting a second or third or even fourth opinion from the research world.
Precisely. They're especially useful when individual studies are small or maybe they have conflicting results.
Right.
By pooling the data, we can increase the statistical power
Okay.
and get a more reliable estimate of the true effect of an intervention.
I'm starting to see why they're so important. I also remember seeing these things called forest plots.
Oh, yes, forest plots.
And meta-analyses, they literally look like a forest.
They do, don't they? But don't be fooled by the name. Forest plots are actually very informative. Each horizontal line on the plot that represents a different study included in the meta-analysis,
Okay.
with the dot representing the study's effect size, and then the line extending out shows the confidence interval.
So the longer the line, the more uncertainty there is.
Exactly. Longer line, more uncertainty.
Okay.
And then at the bottom of the forest plot, you'll see a diamond. That diamond, that represents the overall pooled effect size from all of the studies combined.
So the diamond's like, well, the grand finale, the culmination of all those individual studies.
You could say that. And if that diamond crosses the vertical line of no effect, it means the overall result of the meta-analysis, it wasn't statistically significant.
Okay, so we've decoded forest plots. What about those funnel plots? I remember them being mentioned in the context of publication bias.
Right, publication bias, that's a big problem in research.
Yeah.
Funnel plots are a clever way to visually assess whether there's evidence of that bias in a meta-analysis. Ideally, the plot should look like a symmetrical funnel, with the most precise studies clustered around the top, and then the less precise studies kind of scattered more widely at the bottom.
So if the funnel plot is asymmetrical, it suggests that some studies might be missing.
Yeah, that's right.
Perhaps those with negative or less exciting results.
Exactly. Asymmetry is a red flag. It means publication bias might be at play.
Okay.
We need to be cautious about interpreting the results.
This is all really helpful for navigating all that research out there. What about survival curves?
Oh, survival curves.
I know they're often used in oncology, but are they relevant in orthopedics too?
Absolutely. Survival curves are like stories that unfold over time. They show us the probability of an event happening at different points in time. Like, for example, the probability of implant failure, or maybe revision surgery after a joint replacement.
So each step down on the curve, that represents a bad outcome, like an implant failing.
That's it.
Okay.
And those confidence intervals around the curve, those tell us how much uncertainty there is in those estimates.
So we need to pay attention to those confidence intervals. Wow, we've covered so much already.
Yeah, we have.
From data types and distributions to visualizing data, interpreting research papers, it's clear that statistics are essential for any aspiring orthopedic surgeon. But you know what they say, all work and no play.
Makes Jack a dull boy.
Right. I think it's time for a little break.
Yeah, let's take a pause. Let all this information sink in.
We'll be right back with more insights from the Ortho Made Simple notes, so stay tuned.
See you soon.
All right.
We'll be back in a flash. Welcome back, everyone. Let's jump right back into those key orthopedic statistics concepts.
Yeah, we were just talking about survival curves before the break and how they help us understand that probability of events over time.
Right, right. Like, how likely is it that an implant will fail after a certain number of years, that kind of thing.
Exactly. Now, let's say we're reading a research paper and we come across this term, confidence interval.
Ah, yes, confidence intervals.
What exactly does that mean, and why should we care about it?
Good question. A confidence interval gives us a range of values. And within that range, we think the true effect of a treatment or an intervention likely lies. It's all about estimating how precise the study's findings are.
So it's kind of like saying we're 95% confident that the true effect falls somewhere within this range.
Yeah, that's a good way to put it. And a narrow confidence interval, that means we've got more precise results, while a wider interval, that suggests more uncertainty.
Okay, that makes sense. But how's a confidence interval different from a p-value? They seem to both be related to statistical significance.
Yeah, they're definitely related, but they tell us different things. A p-value tells us the probability of observing the results that we got if there was actually no real effect.
Okay.
So if that p-value is less than 0.05, that magic number, it means the results are statistically significant.
So a low p-value is good.
Right.
It means our findings are probably not just due to random chance.
Right, but it's important to remember that statistical significance doesn't always equal clinical significance. Just because something's statistically significant doesn't necessarily mean it's going to make a real difference for patients.
That's a good point. We always have to think about the practical implications, not just whether something passed a statistical test. Now, I've also heard about these things called type 1 and type 2 errors. What are those all about?
Those are the two ways we can go wrong when we're interpreting study results.
Oh, no.
So a type 1 error, that's also called a false positive.
Okay.
It happens when we reject the null hypothesis when it's actually true. In other words, we conclude there's a difference between groups when there really isn't one.
So it's like seeing something that isn't really there, kind of like a medical mirage.
I like that, a medical mirage. That's a good analogy. And then a type 2 error, that's also known as a false negative, is the opposite. It's when we fail to reject that null hypothesis when it's actually false. So we miss a real difference that's there.
So in this case, we're kind of overlooking a real finding,
Exactly.
like missing a subtle fracture on an X-ray.
Yeah, it's like we're wearing the wrong glasses and we can't see what's right in front of us.
The risk of those errors, is it always there in research?
To some extent, yes, but we can definitely take steps to minimize them.
Okay, good.
For example, using a lower p-value threshold can reduce that risk of a type 1 error, and then increasing the sample size can help to reduce the risk of a type 2 error.
So it sounds like a balancing act.
It is.
Okay, let's shift gears a bit and talk about some concepts that are really important for interpreting clinical trials. I often see terms like risk ratio, absolute risk reduction, and number needed to treat. Can you break those down for us?
Sure. Those terms are all about understanding the impact of an intervention on the risk of an event. So let's start with risk ratio, sometimes called relative risk.
Okay.
That compares the risk of an event happening in one group to the risk in another group.
Got it.
So for instance, if the risk ratio for, say, a complication after a certain surgery is 2, that means the risk of that complication is twice as high in the treatment group compared to the control group.
So it's a relative measure tells us how much more likely an event is in one group versus another.
Exactly. Now, absolute risk reduction, that takes a different approach. It looks at the actual difference in risk between the two groups.
Okay.
So if the risk of that complication is 10% in the control group and 5% in the treatment group, the absolute risk reduction would be 5%.
I think that's really helpful because it gives us a more concrete sense of how big the effect actually is.
Yeah, I agree. Now, what about the number needed to treat, or NNT?
That one I always struggle to wrap my head around.
I know it can be a bit tricky, but the NNT is really useful because it tells us how many patients we need to treat with the intervention to prevent one additional bad outcome.
Okay.
And it's calculated by taking 1 divided by the absolute risk reduction. So in our example where the absolute risk reduction was 5%, the NNT would be 20.
So that means for every 20 patients we treat with that intervention, we can expect to prevent one complication.
Right. It makes it a lot easier to grasp those real-world implications, right?
Yeah, it does. It really helps us weigh those potential benefits against the potential risks and the costs. Speaking of weighing evidence, we talked about meta-analyses earlier, but there's another term that often gets thrown around. Systematic reviews. What's the difference?
A systematic review is a really comprehensive summary of all the available evidence on a particular topic.
Okay.
It follows a very rigorous, predefined methodology to search for, select, and critically appraise all the relevant studies. Now, a meta-analysis, that's a specific statistical technique for combining the results of multiple studies to get that single pooled estimate of the effect.
So you'd say that a meta-analysis is like a specific type of statistical analysis that can be part of a systematic review?
Yeah, that's a good way to think about it.
But not all systematic reviews include a meta-analysis.
Exactly. Sometimes a systematic review might not be able to do a meta-analysis if the studies are just too different from each other.
Okay, that clears things up. When we're trying to make sense of all this research evidence, it's helpful to remember the idea of levels of evidence. Can you remind us what those are and why they matter?
Levels of evidence, that's our hierarchy. It's how we classify different types of studies based on how rigorous their methodology is
Okay.
and how strong the evidence they provide really is. At the top of that pyramid, we've got our systematic reviews and meta-analyses of randomized controlled trials. Those are considered to be the gold standard. They have the highest level of evidence because they're synthesizing data from multiple high-quality studies, minimizing bias.
So the higher up we go on that pyramid, the more confident we can be in those findings.
Generally, yes. But of course, we always have to consider the specific study and its limitations.
Right, makes sense. As we move down the pyramid, what do we see?
Well, then we encounter study designs that are a bit more susceptible to bias,
Okay.
like cohort studies, case control studies, and case series.
And at the very bottom,
At the very bottom, we have expert opinion, which, can be valuable, but should always be interpreted with a bit of caution.
this is all incredibly helpful for, critically appraising research.
It's a crucial skill,
Yeah, and deciding, which studies to really trust.
for sure.
Before we get too carried away, I think it's time for another quick break. We'll be right back soon to wrap up our deep dive into these statistics concepts.
Yeah.
From the Ortho Made Simple notes, which again you can find over at mokiandgrin.sg.
Sounds good. We'll be back in a flash.
All right, welcome back to our deep dive into orthopedic statistics. Still going strong with these Ortho Made Simple notes, which, for those who missed it, you can find at mokiandgrin.sg.
Yeah, it's a great resource.
Tons of good stuff in there.
It really is.
We've covered, a lot of ground, from data types to distributions.
Research papers, bias.
Yeah, all that good stuff. Now let's zoom in on a few more key concepts that I think are definitely going to come up on those postgraduate exams.
Oh, yeah, for sure.
Earlier, we talked about sensitivity and specificity
Right.
when we were looking at those ROC curves.
Yeah.
Could you remind us what those terms actually mean and why they're so important in orthopedics?
Of course. So sensitivity and specificity, they're all about how well a diagnostic test is doing its job. Sensitivity tells us how good a test is at correctly identifying people who actually have the condition.
Okay.
It's like imagine a searchlight. And it's really good at picking out the things we're looking for, but it might also pick up a few other things that aren't actually the thing we're interested in.
So a highly sensitive test is good for ruling out a condition if the test comes back negative.
Exactly.
Like when we order an MRI to rule out a meniscus tear.
Perfect example. Now, specificity, that's the other side of the coin. It tells us how good a test is at correctly identifying those who don't have the condition.
So a highly specific test, That's really good at confirming a diagnosis when the test is positive.
Yes, exactly.
Okay.
Think of it like a fingerprint analysis. If we get a match, we're pretty darn confident in that identification. Choosing the right test, whether it needs to be more sensitive or more specific, really depends on what's going on with the patient and what the consequences are of getting it wrong.
Right, that makes sense. Let's revisit another concept we touched on earlier, inter-observer variability. Why is that so important in research, and how can we minimize it?
So inter-observer variability, it's basically about how much different observers agree on their assessments. It's a measure of consistency. In orthopedics, this could be anything from measuring range of motion to, grading the severity of arthritis on an X-ray.
Right, and if there's a lot of variability between different observers, that can really mess with the results of a study, can it?
Absolutely. If different surgeons are measuring things differently or interpreting things differently, it's hard to know if those differences that we see in the results are real or just due to inconsistencies in how the data was collected.
So how can we try to minimize that inter-observer variability in research?
One key strategy is to standardize those measurement techniques as much as possible. We need to make sure everyone involved in the study is using the same tools, following the same protocols, and interpreting the findings in the same way.
So it's like making sure everyone's reading from the same page.
Exactly.
We've covered a ton in this deep dive, from the
Yeah.
basics of data types and distributions to, really understanding those research papers and being aware of bias. I think it's pretty clear that a solid grasp of statistics is super important for any orthopedic resident who wants to do well on those exams and just in their career overall.
Absolutely, I couldn't agree more. And as you move forward, remember that statistics is a really powerful tool for advancing our knowledge in orthopedics and ultimately improving patient care.
It's not just about passing those exams. It's about using these tools to ask the right questions, interpret research with a critical eye, and make those evidence-based decisions that really benefit our
Well
patients.
said.
So to all of our listeners out there, getting ready for those challenging exams, remember that the Ortho Made Simple notes from mokiandgrin.sg, they're a fantastic resource
They really are.
for mastering these concepts and so much more.
So keep learning, keep asking questions, and keep pushing the boundaries of what we know in orthopedics.
That's right. Until next time, keep diving deep.